Some of the points that will be touched on during this video are how light obeys the law of reflection, how light of different colors can be produced by adding light consisting of the additive primary colors, red, green, and blue, the differences between the three types of mirrors, flat, concave, and convex, how our eyes see different colors, how different objects reflect and absorb different kinds of light, and how light is polarized.
No. Hey, look, it spins like a mirror.
Oh no, now we're upside down!
The reason the camera is upside down is because the concave mirror flips the image. When the light rays hit the concave mirror, they are reflected to a focal point due to the shape, but after they cross the point, they cross over each other, flipping the image. You can see this with how ray 1 is originally at the top and then after the focal point goes to the bottom, and ray 2 does the same thing, with originally being at the bottom and crossing over the focal point to become at the top. The peach area is where the image is right side up before the focal point, and the purple is the image flipped after the focal point.
When I hold the light ray close to the mirror, the reflecting ray stays close to the mirror. And when I bring the light ray up farther into the air, the light ray goes just as high.
The previous experiment is because of the law of reflection. The law of reflection states that with a flat mirror, the angle of incidence has to equal the angle of reflection, and this creates the effect seen in the experiment. The angle of incidence is the angle that the ray makes with the vertical line. The angle of reflection is the angle that the reflecting ray makes with the vertical line.
Notice how the light rays reflect off of the different types of mirrors. This is a flat mirror. This is a convex mirror. And this is a concave mirror.
This is a flat mirror. The rays reflect at the same angle and look the same from where they were started, so the image appears the same size. This is a convex mirror. The incoming rays reflect and turn out, and the reflecting rays make the object appear smaller. This is a concave mirror. The incoming rays reflect and turn into a focal point. This makes the object appear bigger.
Notice how as the mirror approaches the light source, the light rays come together as one. This is because they are approaching their focal point.
On a concave mirror, the rays reflect and meet at a focal point where they become one beam of light. This is shown on the diagram as the red point and the one beam of light in the experiment.
There you go. This is a projector, and it's going to be shooting white light onto our triangular prism. Inside the projector, there is a filter made up of tinfoil, and it has a little slit in it so that a small amount of white light can go through the filter and then attract to the prism. And then when you turn the lights off, you can notice how when the white light hits the prism, it shoots off into different angles, but on the back wall you can tell that the white light turns into all the colors of the rainbow. Okay, this is a light source, and this is a concave mirror, and that's a triangular prism. The light source is going to be shooting off the additive primary colors, which are blue, green, and red, and it's going to hit the concave mirror, and they're going to bounce off, coming together at a focal point right where the prism is. And what you're going to see is the prism is going to shoot off the different colors of the additive primary colors, but it's also going to shoot off white light. So when we turn off the lights, you can notice how white light is produced right here, proving that the additive primary colors make up white light.
White light can be dispersed into its additive primary colors, which means they can also be combined to form white light too. A prism works in a special way to show this. How a prism works is that they refract light as the light enters through one side of the prism at a certain angle, and the glass is made a certain way that it decreases the speed of light. The light is bent inside the prism and hits another one of its faces and emerges out. This is when the dispersion happens and the white light splits into the 7 colors of the spectrum.
All of these fruits reflect and absorb different colors.
An orange is orange because it reflects orange and absorbs all the other colors on the spectrum. A green apple is green because it reflects the green color and absorbs all the other colors on the spectrum. A red pepper is red because it reflects the red color and absorbs all the other colors on the spectrum. The pigments in the fruits are reflecting and absorbing white light from the sun, causing them to appear a certain color. Okay, if you take a red laser pointer and shine it through a red gummy bear, you can see that the light passes through the gummy bear. If you shine the same red light from the laser pointer through the green gummy bear, you can see that the green gummy bear the light does not pass through the green gummy bear. This is because in the red gummy bear, because it is red, it can reflect the red light, allowing the laser pointer to pass through. Because the green gummy bears are green, they absorb the red light, not allowing the light to pass through. This is why we see objects in different colors, because the color reflected by the object is what our eyes see. There are 3 different color receptors in our eyes. Each receptor is called a cone cell and is sensitive to red, blue, or green light, the additive primary colors. Another example of this is a plant that appears green in sunlight but appears black under red light. The green leaf is absorbing all the colors except green. In contrast, an object that reflects no light appears black, which is why when you put a green leaf under red light, it looks black. There is no green light to reflect.
When you combine all the colors of the spectrum, they create white light. However, paint absorbs light. When you add the primary colors of paint together, they don't turn white. They turn a brownish color because they are absorbing all the light and not reflecting any.
Hey, where's the sun?
It's kind of cloudy. Here it is. Well, kind of, but not really. One way to show polarization of light is with a pair of sunglasses. First, you take a pair of sunglasses and you pop out one of the lenses, and then you place it in front of a light source. Now check this out. You can see the light through the sunglass lens. Now when you add the lens we popped out, you can see straight through both. When you rotate the popped out lens 90 degrees, the light is partially blocked out, but until you turn it back like this.
Normally, light travels in waves in different directions. But when you polarize the light, you cause the light to be filtered so that the light travels in waves parallel to each other. The sunglasses have a chemical filter on them made up of polarized molecules. They are horizontally lined up molecules that polarize all light that is traveling on a horizontal plane. When you look at the light through the 2 sunglass lenses, you are seeing horizontally polarized light. But when you turn the popped out lens 90 degrees, it blocks out the light because it is not polarizing it vertically. So by the time the light gets to the second lens, which polarizes horizontally, it filters out this vertically polarized light, blocking the original light.
Here's another variation showing polarization using sunglasses. Take a clear pair of sunglasses and add tape to the inside of one of the lenses, and then take the polarized sunglasses with one of the lenses popped out of it. Now check this out. Take the polarized sunglasses and place them inside the clear pair. Then take the popped out lens and place it in front. As you turn it to 90 degrees, you can see the colors begin to change, and when you turn it back, they change again.
Each time light passes through something, it gets bent slightly. As the light passes through the plastic glasses in the layers of tape, it causes some of the horizontally polarized light to get bent out of its polarized field. When you hold the lenses horizontally, this blocks out certain colors that are no longer polarized on a horizontal plane, which is why the colors change when you rotate the lens.
Be like, no, it's not that one. So everyone, even if you had like 100 hours, you get like a D in the final.
She's watching.